A NASA satellite was in exactly the right place, at exactly the right time. 70 minutes after one of the most powerful earthquakes in modern history, a magnitude 8.8 megathrust rupture off the Kamchatka Peninsula in Russia, a spacecraft called SWAT passed over the Pacific Ocean. And what it captured has stunned scientists. Not because they saw what they expected, but because they saw something they had never seen before. Something that overturned one of the most fundamental assumptions in tsunami science. Something that changes how we understand these waves, how we model them, and, critically, how we warn coastal communities when the next one comes. This is the story of the July 29, 2025 Kamchatka earthquake, the most powerful earthquake on Earth since the 2011 Tohoku disaster that triggered the Fukushima meltdown. Tied for 6th largest ever recorded by modern seismic instruments, anywhere on Earth, since recording began. And it is also the story of what happened afterward, when a satellite that was never designed to study tsunamis accidentally became the most important tsunami-watching instrument in the history of oceanography. Let me take you back to July 29, 2025, 11:24 p.m. Universal Time. It is late evening in Russia, early morning in Japan. The seafloor of the Kuril-Kamchatka subduction zone, one of the most seismically loaded fault systems on Earth, ruptures. The rupture travels along the subduction interface for 390 kilometers. That is 240 miles of seafloor suddenly moving, by up to several meters, in about 60 seconds. The rupture area covered a patch of seafloor 390 kilometers long and 140 kilometers wide. That is 240 miles by 87 miles, roughly the size of the entire state of New Mexico, moving. At shallow depth, just 35 kilometers, 21 miles underground. Shallow ruptures are the ones that slam the hardest. The energy has no depth to dissipate before it reaches the surface. In Petropavlovsk-Kamchatsky, a city of 180,000 people, 460 kilometers from the epicenter, people felt shaking that lasted 4 minutes. 4 minutes! A Kamchatka resident described it to Russian state media. The tremors lasted for 4 minutes. At first it seemed like they were about to stop, but they grew stronger. And then the water came. Within 10 minutes of the rupture, the Pacific Tsunami Warning Center issued its first tsunami threat message. Warnings activated across the Pacific. Japan immediately ordered the evacuation of approximately 1.9 million residents along affected coastal prefectures. 1.9 million people, moving to higher ground. In the middle of the night, tsunami sirens wailed across Hokkaido. Videos showed people taking refuge on rooftops. In Severokurilsk, a small coastal town in the northern Kuril Islands, just south of the epicenter, waves between 5 and 6 meters high crashed into the harbor. That is between 16 and 20 feet. Port infrastructure was destroyed. A fish processing plant was swept away. Boats were torn from their moorings and carried inland. The harbor at Severokurilsk was inundated. Waves reached 200 meters inland from the shoreline. Containers were swept off the docks. A kindergarten near the harbor was damaged. Russia declared a state of emergency in the Severokurilsky district. About 2,700 people were evacuated across the region. And in the steep, narrow valleys along the Kamchatka coast, in Vesnik Bay alone, run-up heights reached 33 meters. 33 meters. That is 109 feet. The height of a 10-story building, water reaching 10 stories high inland from the coast. In isolated Baikovo on Shumshu Island, scientists later measured maximum run-up heights of 10.7 meters, 35 feet. In less populated parts of the coast, American tsunami scientists estimated waves may have reached up to 43 meters, 141 feet. In vegetation surveys, aerial imagery showed trees stripped bare over a half-mile inland. The full damage picture across uninhabited Kamchatka coastlines is still being mapped today. Now, this is all extraordinary. A magnitude 8.8, 6th largest on record, Pacific-wide tsunami, warnings from Russia to Chile, 1.9 million Japanese evacuated. Waves measured across the Pacific. And yet, the biggest story did not come from the waves. It came from space. Further in this video, I want to show you exactly what the satellite saw, why scientists described it as being given a completely new pair of glasses, and what it means for every single person who lives on a Pacific coastline. But first, give this video a like and a hype. Share it. This is the kind of science that deserves way more attention than it gets, and it keeps this channel going. Let me tell you about SWOT. SWOT stands for Surface Water and Ocean Topography. It is a joint satellite mission between NASA and the French space agency CNES, launched in 2022. Its primary purpose was to measure the height of water surfaces across the entire planet. Rivers, lakes, reservoirs, and the ocean. It carries an instrument called CARIN, Ka-band radar interferometer. It works by bouncing radar signals off the ocean surface and measuring the return with extraordinary precision, 1 centimeter precision. And crucially, unlike any satellite instrument that came before it, SWOT measures not just a single narrow line beneath the spacecraft. It measures a swath, a wide sweep, 120 kilometers wide. That is 75 miles of ocean surface measured in a single pass. And at 70 minutes after the Kamchatka earthquake, while the tsunami was still rolling across the Pacific, SWOT passed over the Northwest Pacific Ocean, approximately 600 kilometers from the epicenter. And it captured something that no instrument had ever captured before, a full two-dimensional spatial image of a great subduction zone tsunami from space. The lead researcher on the first major study, Angel Ruiz Angulo from the University of Iceland, described it like this. He said, before SWOT, with the dark buoys that sit on the seafloor, scientists could only see the tsunami at specific points in the vastness of the ocean. And older satellites could only see a thin line across a tsunami in the best-case scenario. But now, with SWOT, we can capture a swath up to about 120 kilometers wide, with unprecedented high-resolution data of the sea surface. He called it a new pair of glasses. And when scientists put on those new glasses and looked at the Kamchatka tsunami, what they saw broke a fundamental assumption of tsunami science. For decades, for almost all of the modern history of tsunami research, scientists treated large tsunamis as what they called non-dispersive waves. Non-dispersive means the wave travels in a stable, unchanging shape, like a single hump of water moving across the ocean at constant speed. The classic mental model. That is how the textbooks have described large subduction zone tsunamis. That is how the warning models have been built. That is the assumption that underlies the forecasts that were used during the 2025 Kamchatka event. And the SWOT satellite showed that assumption is wrong, or at least incomplete, very incomplete. When SWOT captured the tsunami, it did not just see the main wavefront. Behind the main crest, the leading edge of the tsunami, the satellite detected a sequence of trailing waves, smaller, lower amplitude, but measurable, dispersive trailing waves, waves that were spreading out, scattering, varying in amplitude and spacing across the width of the swath. Not a single stable hump of water, a complex, structured, messy wave field, multiple peaks and troughs behind the main front, each with slightly different character. The researcher Ruiz Angulo described the implication directly. He said the main impact for tsunami modelers is that they are missing something in the models they used to run. This extra variability, these trailing dispersive waves, could mean that the main wave is being modulated by those trailing waves as it approaches a coastline. He said the scientific community will need to quantify this excess of dispersive energy and evaluate whether it has an impact that was not previously considered. Let me translate that into plain language. The textbook says the tsunami arrives, the main wave hits, then it subsides. What SWOT shows is that behind the main wave, there is a structured tail of smaller waves that could potentially arrive later from slightly different directions, with timing and heights that the existing models do not accurately predict. For emergency managers, that is critical information, because one of the deadliest patterns in tsunami events is when people see the main wave subside and think it is over. They go back to the shoreline, and then the next wave hits. The 1993 deaths at Mayon in a different context. The 2004 Indian Ocean tsunami, where thousands of people on beaches watched the water recede in curiosity before the waves struck. Understanding the trailing wave structure is not an academic exercise. It is a life and death question. And now, for the first time, we have satellite data that shows us what that trailing structure actually looks like. Now let me tell you about the second study, because a second paper was published in the journal Science in March 2026. The journal Science, one of the two most prestigious scientific journals on Earth. And it found something different from the first study, but equally stunning. This team, led by Ignacio Sepulveda from San Diego State University, with colleagues from Scripps Institution of Oceanography and other institutions, focused specifically on where those dispersive trailing waves came from. And they traced them to a very specific part of the earthquake rupture, the part closest to the trench, less than 10 kilometers beneath the seafloor of the Kuril-Kamchatka Trench. The trench is where the Pacific Plate dives beneath the Okhotsk microplate. It is the deepest part of the subduction interface. It is also the hardest part to monitor. Seafloor pressure sensors, the dart buoys, sit on flat ocean plains and sense pressure changes as the tsunami passes overhead, but they cannot tell you which part of the fault caused the wave. Seismic networks on land can measure how the earthquake ruptured, but for the near-trench portion, the shallowest, outermost zone of the fault, land-based seismology has limited resolution. The trench is where the fault is shallowest, and slip near the trench tends to generate more efficient tsunamis. Less energy is trapped underground. More goes into the water column. This is what happened in the 2011 Tohoku earthquake, where the rupture reached all the way to the seafloor surface, where the tsunami became catastrophic. And the SWAT satellite, with its 1 centimeter precision measurement of sea surface height, was able to capture the dispersive trailing waves that were specifically generated by that near trench slip, and trace them back to within 10 kilometers of the trench. The researchers combined SWAT data with DART buoy data and Sentinel-1A INSAR, satellite radar measurements of ground deformation, to pin down the rupture model with unprecedented precision. Their preferred model placed the peak slip concentration near 50.5 degrees north, 158 degrees east, with the rupture concentrated between 49.5 and 52.5 degrees north along the subduction zone. They confirmed the rupture extended closer to the trench than earlier seismic-only models suggested. Alice Gabriel, associate professor at Scripps Institution of Oceanography and co-author on the science paper, described it directly. She said capturing this tsunami with SWAT near its source gave the team crucial data on the earthquake rupture, how it generated the resulting tsunami, and the physics playing out near the trench. Near the trench. That is where the worst tsunamis are born. And for the first time, a satellite told us exactly what happened there. Now, I also want to tell you something that is barely being covered anywhere. The SWAT satellite was not alone in observing this tsunami from space. A second satellite, Sentinel-3A, crossed the tsunami front approximately 30 minutes after the earthquake, about 570 kilometers from the source. Sentinel-3A is a European Space Agency Earth observation satellite. It carries a radar altimeter. The nadir-only measurement, a single line rather than a wide swath, picked up both the leading crest and the dispersive trailing wave packets, independently, consistent with what SWAT saw. 2 independent satellite observations, both confirming the dispersive wave structure. The dispersive trailing waves were measured at 20 to 50 centimeters in amplitude, 8 to 20 inches, placing them 7 to 17 times above the noise floor of the instrument. Not noise, not instrument error, real waves, measurable waves. Complex structure in the tsunami wave fields that the models had not been predicting. And there is one more layer to this story. Because SWAT had actually seen this kind of dispersive behavior before, not from a magnitude 8.8 earthquake, but from smaller events. The researchers noted that SWAT previously observed dispersive tsunami waves near the Loyalty Islands on May 19, 2023, and again following the May 2, 2025 magnitude 7.4 Drake Passage earthquake. 3 separate detections now, 3 different events. And the conclusion from that pattern is significant. The researchers proposed that dispersive tsunami signals may be more common than previously recognized, that past gaps in detecting them were not because they were rare, but because the instruments were not good enough to see them. Before SWAT, the tools were simply insufficient. Now they are not, and the universe of tsunami physics is larger than we thought. Let me put this all in historical context. Because the Kamchatka region has a long and terrifying history with tsunamis. November 5, 1952, a magnitude 9.0 earthquake struck the same Kuril-Kamchatka subduction zone. In Severokurilsk, the same town that was flooded in 2025, the 1952 tsunami was catastrophic. Wave heights reached 15 to 20 meters. The town was completely overtopped. At least 4,000 people perished. The entire town was swept away. After 1952, the survivors rebuilt Severokurilsk on higher ground, further from the harbor, elevated above the 1952 inundation line. And that decision, made 73 years ago by people who had survived the worst, is part of the reason why in 2025, when the tsunami hit that same town, there were no deaths. Because the lessons of 1952 were literally built into the landscape. The harbor was damaged, the fish processing plant was swept away, boats were scattered, but the people were above the water. That is what good tsunami science and good community planning based on that science can do. Now imagine what SWAT-level understanding of tsunamis could add to that. More accurate wave timing, better prediction of trailing wave sequences, tighter mapping of which parts of a fault are responsible for the worst coastal impacts. The NOAA Center for Tsunami Research already used the Kamchatka SWAT data to validate its forecast models, comparing what the satellite observed to what the models predicted, identifying where the models diverged, understanding why, and building better models for the next event. Because there will be a next event. The Kuril-Kamchatka subduction zone produces major earthquakes roughly every century. The Pacific Plate moves northwest and dives beneath the Okhotsk microplate at 79 to 86 millimeters per year. That stress accumulates. It will release again. And the Cascadia subduction zone off the US and Canadian Pacific coast is a similar system. Same plate dynamics, same potential for megathrust earthquakes. The 2025 Kamchatka event, the earthquake that triggered the new satellite studies, is therefore not just a Russian story. It is a lesson for every Pacific coastline on Earth, for Hawaii, for Alaska, for the Pacific Northwest, for Japan, for Indonesia, for every community that lives near a subduction zone. What SWAT showed us is that the tsunami warning systems we have built over the past 70 years, since the 1952 Kamchatka event led to the creation of the first Pacific-wide tsunami alert network, are good. They worked in 2025. 1.9 million Japanese evacuated. No casualties in Japan. No casualties in Hawaii beyond minor property damage. The warning system worked. But it can get better, and SWAT is showing us how. One more thing that I found extraordinary in all of this. Not only did satellites track the tsunami across the ocean surface, the tsunami was also tracked in the ionosphere, the upper atmosphere. A separate scientific study published in March 2026 in a journal on space physics found that as the tsunami waves propagated across the Pacific, they generated atmospheric gravity waves, pressure disturbances that rose upward through the atmosphere. Those disturbances reached the ionosphere, the layer of charged particles 80 to 1,000 kilometers above Earth. And GNSS satellites, the same network that powers your GPS navigation, detected those ionospheric disturbances propagating at speeds that exactly matched the tsunami's advance across the ocean. Scientists detected the ionospheric signal at Mauna Kea in Hawaii approximately 20 minutes before the local tsunami arrival. 20 minutes. from the upper atmosphere before the wave hit the shore. This is not science fiction. This is what happened in July 2025. A tsunami generated by a magnitude 8.8 earthquake sent ripples not just across the ocean's surface, but all the way into the upper atmosphere. And satellites detected both, from above and below. Every single instrument pointing at this earthquake and its waves from space, each one telling us something new, each one adding a layer of knowledge that the generation before us simply did not have. This is where we are now. This is what modern geoscience looks like when a great earthquake strikes. And the researchers who published in Science said it plainly. This helps improve our understanding of earthquakes that rupture close to the trench and helps coastal communities better prepare for the seismic and tsunami hazards they face. We are not helpless in the face of these events. We are learning, faster than ever, with better eyes than ever, from space, from the seafloor, from the atmosphere, all at once. I will be watching this story continue to develop. The models built from the Kamchatka SWOT data are already being refined. The next papers are already in preparation. Check out the end screen for more on the seismic systems that threaten the Pacific right now. The Earth is not quiet, and our eyes on it have never been sharper. Stay safe, guys. Be aware. Look up, look down, look left, look right. Anywhere, basically. Bye-bye.